All right, so far in our journey, we've gotten really good at talking about how things move from point A to point B. Translational motion. But if you look around, the universe doesn't just move in straight lines, it spins. So today, we're diving headfirst into the incredible mechanics of rotation.
Think about it. We have a solid toolkit for a ball flying through the air. But what about a planet spinning on its axis, or a wheel on a car, or even a figure skater pulling into one of those dizzying pirouettes? It kind of feels like we need a whole new set of physics rules, right? Well, what if we don't? What if we could just translate the rules we already know into a new language?
Okay, so let's jump right in. The very first step is to learn the language of rotation. And you know what the best way to do that is? We're going to see how it perfectly mirrors the language of linear motion that we already speak fluently.
And this is what's so cool. Look at how clean these parallels are. For every single concept we have in the linear world, position, velocity, acceleration, there's a direct counterpart in the rotational world. It's almost like learning a new language, where all the important words sound almost the same. It's fantastic. First up, instead of linear position, which we call x, we have angular displacement, which we call theta. This isn't about how far you've gone in a line, it's about how much you've turned. And we measure this in radians. Now there's a reason we use radians. They are the natural unit here, because they neatly connect the arc of a circle to its radius, a connection that you're going to see is absolutely crucial.
Makes sense, right? So next, instead of linear velocity v, we talk about angular velocity, omega. This is exactly what it sounds like, how fast something is spinning. It's just the rate that your angular displacement, your theta, is changing over time.
And you can probably guess the last one. Linear acceleration, a, has its twin, angular acceleration, alpha. This tells us how quickly an object's spin is speeding up or slowing down. And here's the best part. All those kinematic equations we mastered for constant linear acceleration, they work perfectly with these new angular variables. We just swap them out.
So, here's the million-dollar question. How do we actually connect these two worlds? How do we get from the angular speed of a spinning tire to the linear speed of the car? The bridge, the absolute key that unlocks everything, is the radius r, the distance from the axis of rotation.
And this slide just shows you how it works perfectly. Any single point on a spinning object actually has two different kinds of linear acceleration happening at once. First, you've got tangential acceleration. That's the one that changes the point's speed. And then you have radial acceleration, which is always pulling it inward, constantly changing its direction to keep it moving in that perfect circle.
Okay, we've got the basic language down. Now let's get into the dynamics. And you're going to see a pattern here, because those familiar ideas of mass and force, yep, they have direct rotational equivalents too.
So instead of mass, which is just an object's resistance to being pushed in a straight line, we have something called rotational inertia, which we write as I. It's an object's resistance to being spun. Think of it as the rotational mass, or the laziness of an object when it comes to spinning.
But, and this is a huge but, here's the critical difference. Mass is just mass. A kilogram is a kilogram. Rotational inertia, though, cares deeply about how that mass is spread out. The farther away the mass is from the axis of rotation, the harder it is to spin. And that's where this handy tool called the parallel axis theorem comes in. It lets you calculate the inertia around any axis if you already know the inertia around the center of mass. You just add on this extra term, mh squared, which accounts for moving that axis. It really shows you how much that distance matters.
So, let me ask you this. You've got a solid disk and a thin hoop. They have the exact same mass. Which one is going to be harder to get spinning? It's the hoop, every single time. Why? Because all of its mass is way out at the edge, as far as it can be from the center. That gives it a much higher rotational inertia.
And what actually causes something to start spinning in the first place? Well, it's not a force exactly, but a torque, which we represent with the Greek letter tau. Torque is the rotational version of force. The best way to think about it is using a wrench on a bolt. You apply a push, a force, but you do it at a distance. That combination of force and distance creates the twist. That's torque. Okay, we have all the pieces on the board now. We've got rotational acceleration, we've got rotational mass, and we have rotational force. So now we can put them all together into the single most important equation in all of rotational dynamics.
And there it is, Newton's second law for rotation. Just look at that beautiful symmetry. On one side, you've got F equals ma. On the other, you've got torque equals I alpha.
It's the exact same relationship, just spoken in our new rotational language. This is what's so powerful. We have one unified framework that helps us understand all kinds of motion, whether it's linear or spinning. So now that we have this complete system for the dynamics of rotation, what can we do with it? Well, let's apply it to one of the most powerful concepts in all of physics, energy.
We all know that an object that's moving has kinetic energy. Well, it turns out an object that's just spinning in place also has kinetic energy. We call it rotational kinetic energy. And just look at that formula, 1/2 I omega squared. It's a perfect analog to 1/2 mv squared. It just makes sense.
And this isn't just some abstract idea. This is real, measurable, usable energy. For instance, that number you see on the screen, over 1,000 joules. That's the energy stored in a pretty small 1.25 kilogram cylinder that's just spinning really fast. Now, to put that in perspective, that's enough energy to lift a 220-pound person about 3 feet off the ground. All of that power just stored in its spin.
So what does this do to our big, beautiful laws of conservation of energy? It's actually super simple. We just add a new term to the list. When we're doing our energy accounting for a system, we now have to check for translational kinetic energy, potential energy, and rotational kinetic energy. Our toolkit just got an upgrade. So let's just take a step back and appreciate what we've done. We have built an entire framework for understanding rotation, and we did it by just drawing direct analogies to the linear motion we already knew. From kinematics to dynamics to energy, every single piece has a rotational twin. We didn't really learn new physics, did we? We just learned to speak a new, rotational dialect of the physics we've known all along.
This framework is incredibly powerful, but of course, it leads us to the next big question. We've tackled pure moving, and now we've tackled pure spinning. But what happens when an object does both at the same time, like a rolling wheel, or a bowling ball heading down the lane, or a planet orbiting the sun while it spins? Well, that's exactly where we're headed next.